For this chapter 4, section 3, we are going to look at the differences between actual yield, theoretical yield, percent yield, and then how to calculate percent yield for the reaction. And what's great is you already know how to find theoretical yield, because theoretical yield is how much product can be expected mathematically based on our stoichiometry. And in our last section, we had two different reactants and we found how much product could theoretically be formed. This was reactant 1, reactant 2. We went grams to moles, moles to moles, moles to grams, and we got two different amounts of product. One of them was a bigger number, one of them was a smaller number. That smaller number is how much could be produced, and we knew that whatever was attached to that was our limiting reactant. So I'm going to say LR, limiting reactant. This is our theoretical yield. We obviously can't make, if this is the bigger number, we can't make more of something than this number allows us to. Now, actual yield is when we are doing the experiment in lab and we actually measure how much product was gathered at the completion of the reaction. So actual yield is in the lab, how much did you actually measure? Theoretical is doing stoichiometry to figure out theoretically how much could we get. And then percent yield is the measure of the extent of the reactions by taking actual divided by theoretical and timesing that by 100%. Now, can we ever get 100% or more than 100%? I mean, it can't get greater than 100%. Could we get exactly 100%? Doubtful. The amount of product that you would expect to get, usually our actual yield is less than the theoretical yield because of several reasons. We could have impure reactants, we could have other byproducts produced, we could have an incomplete reaction, or you could have lost product by human error. For example, let's say that I was making a pizza and this pizza, 100% of this pizza would be 4 slices. Okay, so I'm pulling the pizza out of the oven and one of the slices falls off face down on a dirty floor. You actually have 3 pieces of pizza as your final product. So my actual would be 3. My theoretical, I should have theoretically had 4. So I would have a 75% yield because I would do my actual 3 divided by 4. So simply just by losing product, your actual yield is less than your theoretical. We could have measurement errors when it comes to, let's say we measured filter paper with a certain product on it and you did your subtraction wrong. So let's do a quick problem here and figure out what the limiting reactant is, figure out our theoretical yield, and then figure out what our percent yield is. In this case, we're told that we have 50 grams of aluminum and 50 grams of oxygen. And we are told that our product is aluminum oxide. What is our theoretical yield? Well, I'm going to start with my 2 reactants. I got to write our reaction first. So I've got aluminum plus oxygen to give aluminum oxide. And again, I would have started with just aluminum plus O2 to give me Al2O3. I would have said, oh, the right side has 2 aluminums, so I need a 2 over here. 3 oxygens versus 2 oxygens. I would have thought, oh, let's get to 6. So 3 here, that gives me 6 O's. A 2 here would give me 6 O's, but that gives me 4 O's, so I'm going to cross this off and put a 4 there. So we have a balanced equation now. Then I'm going to start with my 50 grams of aluminum, and I'm going to figure out how much product could be formed. Follow with me through this. I started with 50 grams of aluminum, so I'm going to go grams to moles for my first step. Looking at the periodic table, that's how many grams are in 1 mole of aluminum. Then I'm going to compare my mole to mole ratio. 4 moles of aluminum to 2 moles of aluminum oxide. So that took me to the aluminum oxide. Then I've got my moles of aluminum oxide to grams of aluminum oxide. So with 50 grams of aluminum, I can produce 94.3 grams of aluminum oxide. Now let's do the same thing with our other reactant, the 50 grams of oxygen. So again, I've got 2 oxygens, so 2 oxygens is 32 grams. So I went grams to moles of oxygen, so that's a 3 moles of oxygen to 2 moles of product. And then that same last piece here, notice that these are equal, moles to grams of aluminum oxide. So notice I have 2 different product amounts. Which one is the correct answer? Can I make 94.3 grams of product or 106.2 grams of product? And obviously we know that I am limited by the aluminum over here. I cannot make 106 grams if I only have enough aluminum to make 94.3 grams of aluminum oxide. So this is our theoretical yield. We'll say TY. That number that we got via stoichiometry is our theoretical yield. Now we were told, it said, well, what if 48.5 grams of aluminum oxide was collected at the completion of the reaction? That's our actual yield. What is the percent yield? Well, then all you do is actual divided by theoretical, and the theoretical we got from the slide before. This is stoichiometry, and this we were told in this case, because we weren't in the lab, we were told that here is how much was collected at the end of the reaction. So actual divided by theoretical times by 100%, and we get 51.4%. Let's look at another example. Let's say I have 10 grams of gold and 10 grams of chlorine. They're sealed in a container, heated until the reaction is complete. The product is gold 3 chloride. We want to know what the limiting reactant is, what the mass of gold chloride formed is, and the mass of the reactant in excess. So first we need to write our equation. Gold plus chlorine gives me gold 3 chloride. Remember, Au3 means plus 3 and chlorine is minus 1. So to have a neutral compound, we need to have 1 of these plus 3's and 3 minus 1's. So AuCO3. Now we need to balance it. Okay, hopefully you have this. Now what? We have 10 grams of each reactant. 10 grams of Au and 10 grams of Cl2. Why don't you pause the video to see if you can work through to see how much gold chloride would be produced, and we'll come back to check our answers. Let's see how you did. I started with 10 grams of both of my reactants. I looked on my periodic table to figure out the molar mass of Au, and there's only 1 Au. So in 1 mole of Au, 196.97 grams. I looked at my mole to mole ratio of Au to AuCO3, so it was a 2 to 2 ratio. And then I went from moles to grams of AuCO3. When I did all of that, and when you do your total top divided by your total bottom, I got 15.4 grams of product. Looking at chlorine, start with 10 grams of chlorine. Again, that's Cl2, so 2 chlorines is 70.9 grams and 1 mole of Cl2. It's a 3 moles of chlorine to 2 moles of product, and then the same moles to grams of AuCl3. And I got 28.5 grams. So how much is my theoretical yield? Again, it's always my smaller one. So my limiting reactant is our gold. Now it wants to know how much excess there is. So it wants to know how much excess chlorine we have in this reaction. So remember, we always start our last bit of stoichiometry. start with what I'm limited by, the 10.0 grams of gold. I'm going to go grams to moles, just like I did here. What's great about this third part is all of the information you need is already here. So I'm going to just say my 196.97 grams of gold and 1 mole of gold. Now remember, I'm going from reactant to reactant in this case. So I'm going from gold to chlorine. So 2 moles of gold to 3 moles of Cl2. And then 1 mole of Cl2, we know its molar mass is 70.9 grams of Cl2. This is going to tell me how much chlorine do I need to completely use up my gold. When I plugged and chugged, I got 5.40 grams of chlorine used up. Now remember, we started with 10 grams of chlorine. So to figure out how much excess I have, 10 grams minus 5.40, and I should get an excess of 4.60 grams. Here's another one for you to try. See if you can set this up. Determine the limiting reactant when a mixture of 5.00 times 10 to the 3rd grams of silicon dioxide and 5.00 times 10 to the 3rd grams of carbon react. What is the theoretical yield of silicon carbide? So this is our product that we're trying to see what our theoretical yield is. Why don't you pause the video, set it up. Here's my work. See how you did setting it up. The number one thing hopefully you remembered was that we needed to balance our chemical reaction here. So I started with 500 grams of both my reactants. I went grams to moles for both of them. My moles to moles for the silicon dioxide and the silicon carbide were 1-to-1 ratio. But I had 3 moles of carbon for every 1 mole of silicon carbide. And then moles to grams. I got 333 for the first one and 555 for the second one. So obviously my theoretical yield is going to be my lower amount. How about this one? DDT is an insecticide banned by the U.S. government because of its hazard to fish and birds. It can be prepared as follows. Chlorobenzene plus chloral to give us DDT and water. So we're told if we have 451 grams of my chlorobenzene, so here's this much, there's that much of chlorobenzene, reacts with 368 grams of chloral. So we are told the actual yield. We're told how much it actually made. Determine which species is the limiting reactant. Calculate the theoretical yield. So we need to figure out stoichiometry. How much could we get from both of these reactants theoretically? We're told how much we actually got. So then we can find our percent yield. Why don't you try to set it up? All right, let's see how you did. I started with the 451 grams of the chlorobenzene. And then I started at the same time the 368 grams of the chloral. The first thing I did was find the molar mass of both of those, so I could go from grams to moles. That was my first step for both of those. Now notice I normally have my labels, but I didn't because I was running out of room. But you should always have your labels so that we know what we're looking at. So I went grams to moles for both. Then I looked at my mole to mole ratio. So my first one, my chlorobenzene, was a 2 mole of chlorobenzene to 1 mole of DDT. And my chloral to DDT was a 1-to-1 ratio. And then I found the molar mass of DDT, 14 carbons, 9 H's, and 5 chlorines. I got 254.25 grams. So moles to grams. I got 795 grams for my first reactant, 862 grams, which we know we can't make more than what this allows us to. So we were told our actual, which is 507, this is our actual, divided by our theoretical, which would be what we got stoichiometry-wise, times by 100, I got 63.8%. Here are 3 join-ins for you to try. Pause the video, see if you get the same answer. Moving on to section 4, we're going to look at analyzing a mixture of compounds with stoichiometry, and we're going to be able to find empirical formulas for an unknown compound, also using stoichiometry. Let's look at this chemical analysis. We first start with a sample containing an unknown amount of the sulfate ion. Here it's sodium sulfate. And it's analyzed adding barium chloride. So I've got sodium sulfate, my clear solution, and I have barium chloride, both aqueous solutions. When barium chloride is added to the solution, barium sulfate is precipitated. If we looked at our solubility rules, we would see that this forms a solid precipitate. Now this solid is collected in filter paper, so we're able to pour out this solution into here, and the aqueous solution goes through and the precipitate will get left behind in the filter paper. So then we can dry that barium sulfate. We knew the mass of the filter paper before we started. It's not damp at all. We can weigh that solid barium sulfate and determine that mass. Here's a situation where I'm told that I have a sample of a mineral that contains sodium sulfate. That sodium sulfate is converted into barium sulfate. Okay? The mass of the recovered barium sulfate we are given. What is the mass percent of sodium sulfate in the mineral? Well, let's look here. We're going to assume that all of the sulfate in sodium sulfate ends up as barium sulfate. So let's look at sodium sulfate. Let's say we're starting with Na2SO4. We know that that's the compound because that's +1, this is -2. And we said that we added barium chloride to it. We're going to have a double replacement reaction. So we would have sodium chloride, and we would have barium sulfate. Then we need to balance our equation. 2 sodiums on the left, so we need 2 sodiums on the right. There's 2 chlorines here, 2 chlorines there, 1 barium, 1 barium, 1 sulfate, 1 sulfate. Okay, so now we can find moles and mass of sodium sulfate, because if we know the mass of barium sulfate, if we know grams, we can get to moles. And if we know moles of barium sulfate, we can convert moles to moles by looking at our mole ratio. So here's our pathway. Grams of barium sulfate to moles of barium sulfate. Moles of barium sulfate to moles of sodium sulfate. Moles to grams, and then we can find the percentage of Na2SO4. Let's do it. So we were told that we recovered 0.177 grams of barium sulfate. So 1 barium, 1 sulfur, and 4 oxygens molar mass, grams to moles. It was a 1-to-1 mole ratio, and the molar mass of Na2SO4 is 142. So that means that we started with 0.108 grams. So we're going to take that 0.108 divided by the 0.123. I'm going to back up the slides here, because we were told that we had a 0.123 gram sample. So that's the full amount that we started with. But we found mathematically that we ended up with 0.108. So our part divided by our whole times it by 100, 87.8% of sodium sulfate. Next, we can determine the formula of a hydrocarbon by combustion reactions. Now, combustion involves the addition of oxygen. You know that. It's a hydrocarbon plus oxygen to give us carbon dioxide gas and water vapor. Always, always. So let's look at this example. If I'm told that I have a sample of a compound that contains carbon, hydrogen, and oxygen. I don't know how many of each. We combust it. Our results, if I know how many grams of CO2 and how many grams of H2O, how can I find out what my formula is, my empirical formula? Empirical means a reduced formula. And if we're told the molecular weight of the compound, how do we find out that molecular formula? Well, let's look. I was told how many grams of carbon dioxide I ended with. So we're going to go grams to moles of carbon dioxide. And then see how many moles of carbon that is. So we were told this is how much product CO2 I had, grams to moles. Now in CO2, in 1 mole of CO2, there is 1 carbon. Because remember, however many carbons are on the right is how many carbons I need on the left, right? So if I have a hydrocarbon compound, we said it was hydrogen something, carbon something, oxygen something, plus O2 to give me CO2 and H2O. However many carbons are on the right is how many carbons I need on the left. So let's look at that mole to mole ratio. So we went grams to moles, moles to moles. I get how many moles of carbon there are. Now we were also told how many grams of H2O. Okay, so I'm going to take my grams of H2O and go grams to moles. And then in H2O, we know there's 2 H's. Now notice that I'm doing this for carbons and I'm doing this for H's. I'm not including the O's yet because notice that there's oxygen in 2 different places on the right. There's oxygen in 2 different places on the left. So I'm holding off on that. All right. So like I just said, there's no way to know how much of that oxygen came from the sample versus the oxygen. So we're not going to do this directly. We're going to do it indirectly. We know that our original sample mass was 1.516 grams, and that includes the carbon, the hydrogen, and the oxygen. But remember we just said in this last slide, I couldn't take my grams of CO2 and grams of H2O and do the same thing that I did because there's O's in both of them, and I don't know how much oxygen I used here. So I can't just say however much I got here would be my mole ratio for this. However, if I know how much carbon and hydrogen were in my products, I can find out that ratio. And if I know how much original sample I had minus that carbon and hydrogen mass, I can get the mass of oxygen that's in that compound and then go from grams to moles to figure out moles of oxygen. So I simply took the moles of carbon and moles of hydrogen from the slide prior to this, and I went moles to grams, all right, for carbon and hydrogen. Now, let's take our original mass minus the carbon and the hydrogen mass. That's my grams of oxygen. Now, what can I do with grams of oxygen? I can get to moles of oxygen. Remember, this is just single O. It's not diatomic. It's not by itself. It's in a compound, so it's just O. Okay, now I know moles of oxygen, moles of hydrogen, moles of carbon. And what can I do if I know all of those moles? How do I get whole number ratios? Well, I divide them all by the smallest number, right? So I take my smallest number should be that 0.0473. So divide them all by 0.0473, and I should get 1 carbon, 4 hydrogens, and 1 oxygen. All right, we know its empirical formula. Next, let's find out what that empirical formula mass is. Let's add up 1 carbon, 4 H's, and 1 O. Because if I know that empirical mass, and I'm told the molecular mass, I can do that molecular mass divided by empirical mass to get a whole number ratio. So let's look. We were told that the molecular mass was 160.2 grams. Well, if I add up 1 carbon, 4 H's, and 1 O, I get an empirical mass of 32.04. So that goes down there. So 160 divided by 32-ish should give me about 5, which means I'm going to multiply everything in CH4O by 5. So 5 carbons, 20 H's, 5 O's would be my molecular formula.